Welcome back, Speezers. We're going to be talking about how to use algebra tiles and when we're going to be able to not use algebra tiles. Great tool. Let's figure out what limitations it has. Algebra tiles are described by the number 2 at the bottom of your screen. So a small plus sign means a positive constant. A long positive means it's a positive variable. A small negative or minus sign means it's a negative constant, and a long negative means it's a variable. So let's see how we can use that. So at this point, I've substituted my algebra tiles into, I've substituted my expression into algebra tiles. So let's take a look here. This b is positive, and so I rewrote it as this long plus sign. Then this 6 is negative. Really, it just means that I have 6 negatives. So I wrote it as I'm having 6 negatives. Then I have 2 positive b's. Well, b is a variable, so I do a long plus sign, and I have 2 of them, so I do 2. And lastly, I have the positive 3, so I wrote down 3 positives. By doing this, it allows me to kind of regroup. So something like the commutative property limits us. It says that the order of subtraction matters. But a fun little way around that is the commutative property also states that the order of terms does not matter. So as long as I move them as terms, I can move this entire group wherever I want to. So I'm going to put them over with the other constants. Now, if I notice, I have 3 positive b's, indicated by the long pluses. I have 3 of them, and it started out as b, so it's got to end up as b. Then I need to remember my 0 pairs rule. That means for every positive and negative that match, they cancel each other. So if I go through and I cancel, now all I gotta do is look at what is left. Here I have 3 left. But I also gotta remember that it's 3 negatives. Now when I bring this all back together, I will get a final answer. And that final answer is just gonna simply be 3b minus 3. And now I have been able to simplify the original expression by turning them into algebra tiles, moving them to where longs are with longs, shorts are with shorts, use 0 pairs to cancel, that's what combining like terms are, and then I translate it back into algebraic form. As you can see, I've already started on the second example here, but something to take into account is this 2. It's telling us how many of what's in this group I have. So really it's telling me I have 2 of the same f's and 2 of the same negative 5's. So what I do here is I just double what I have. That's all 2 means. Because remember, the distributive property just means it's multiplication. And we multiply what's in groups by taking the coefficient and multiplying it by each term inside. And let me correct myself. I don't mean coefficient. I meant to say the leading factor. I'm just used to saying coefficient, so I apologize. Alright, so now I've rearranged so that longs are with longs, shorts are with shorts. And because I rearranged, I went ahead and found my 0 pairs where negatives and positives pair up to equal 0. By counting what's left, I find that there are 3 positive f's, and I forgot to go ahead and write that as a positive. Don't have to at this point, but it's still good practice. And then I'm going to bring it together for a final answer. After combining those 3 f's with the 7 negatives, I get 3f minus 7. So one way to do the distributive property is how we've seen it before. We just do it by algebraically by taking the leading factor outside and multiplying it by each term inside. I've illustrated that on number 3. Here, we hit one of our limitations of algebra tiles. We could do this in algebra tiles, but we would have to write 18 individual plus signs. That's a lot. The larger our numbers get, the harder it's going to be able to use algebra tiles. It's not that it's impossible, it's just going to take more time than if we did it otherwise. So I do want to go through and identify my terms and my like terms and combine them. As we've learned before, I identified my terms. This time I boxed them in, and then I brought together via the lines the like terms to end up with 26 positives and 4 negative j's. With that said, j normally as a term would be written first, but since it's negative, we kept it where it was. Now, before we really get going with fractions, I want to bring to the attention that 2e over 3 is the same thing as 2/3 times e. It's going to be important to be able to know that these two are interchangeable. So if you see something in the numerator, that's being multiplied, in other words, it's a factor, you could just write it as being multiplied by the fraction it's being multiplied by. Now, with fractions talked about here or seen, let's add these to the list of limitations of algebra tiles. There are ways to make algebra tiles and write them, but here's my question to you. How would you write 2/3 of an algebra tile without it looking like a regular algebra tile? Or without it looking like something completely brand new? That's the hard part. So, understanding that algebra tiles absolutely has its uses and we can use it to think through the problem, we still need to be able to do it algebraically, because algebra is what allows us to actually do the adding, subtracting, multiplying, and dividing we've always been used to. So, for example 4, we went ahead and distributed our leading factor of 1. That just meant that this line here is the example of that. We took 1 times 2/3 e and 1 times -1/2. Then over on the second group, we took 1 times 1/3 e and 1 times 5/8. Then we got those answers, defined them as terms, brought them together as like terms, and simplified all of our answers back into an expression, just like we have been doing throughout this section.